no big deal. So a chemical equation identifies the starting and the finishing chemicals as reactants. We start with reactants and we end up with products. So reactants are on one side of the arrow. They react with each other, and as they do, they generate products. Think about this little arrow almost like an equal sign, right? Now, when you do this, and when you observe this in the lab in nature, you need to understand that not all reactants or products may always be visible. If you burn something in air, you don't see the oxygen that goes into the burning reactions. Or your solutions may be totally clear, you can't see it. But there are reactants and products that are involved in these chemical reactions. I'm going to give you some example. The reaction of potassium with iodine. How would this work? K plus I on one side. These are my individual reactants. Make a product, a compound, that's Ki. And that works because, remember, +1, -1, push it together. And here I have my chemical equation. Right? Now, chemical equations are balanced. They need to reflect the conservation of charge and also the conservation of mass. How does this work? So every single atom that reacts must be accounted for, both in the reactant part, right, on this side of the arrow, and in the product part on that other side of the arrow. And we're going to walk you through this a little bit as a background. So chemistry, one semester of chemistry in one lecture session. That's something. All right. Balancing the equations, how does this work? Remember gas rule, non-noble gases come in pairs. Right? Elemental gases other than noble gases come in pairs. Let's try a reaction. We're going to burn some hydrogen gas, and the way we're going to do this is we're going to have some oxygen and some hydrogen, and we ignite it coming out of two pipes. We're making lots of water molecules, something like that. Here's my, I would have done it the other way around. These little tiny things supposed to be my hydrogen gas, and these red things are the oxygen gas, and you can see they come in pairs, kind of move in pairs right up there in my animation. So what we're going to do first is we're going to write down the reactants. What do we have? What reacts here? Well, we have hydrogen, definitely, and we also have oxygen. Yeah, but wait a minute. Hydrogen, what about the gas rule? Comes in pairs, H2. You can see that right here, right? And oxygen, hydrogen needs to react with something. That is our oxygen, also comes in pairs. Is the O2. So let's write it down kind of in a raw formula. So H2 plus O2, put those two together. What are we getting on the other end? What is the product we're predicting this reaction makes? And this reaction makes is, of course, water. So we can write down the correct chemical formula for water, which means subscripts must be correct. Piece of cake for water, so it makes H2O. But we have a problem now. Hope you can see this. 2 hydrogens here, 2 hydrogens on this side. 2 oxygens here, only 1 oxygen on this side. So something is wacko, and we need to fix that. All right, let's use this equation and start to balance it. And really, balancing the equation is we need to have each atom to be accounted for, which means atoms on the left side of the arrow must be the same number as the atoms on the right side of the arrow. We cannot lose one or we cannot gain one within the arrow somehow magically. Think about the arrow being the equivalent to an equal sign in math. When you do math, things on the left side must be the same as things on the right side of that thing. All right. To show you this, that it's really a balancing act, we're going to draw a scale. Right there. Fulcrum, a scale, and we're going to park these globs or things on their correct side. Now, the fulcrum here is my little equal sign or that arrow. That's the fulcrum. It separates this side from that side. So whatever we have on this side needs to go on this end of the scale. Whatever we have here needs to go on this side of the scale. So we're going to do this. I have 2 hydrogens and 2 oxygens here, and I have 1 H2O on that side. Now the question comes, which side of the scale is heavier? Well, you can see this, we have a little surplus there, and so we are not balanced. We're tipping to one side. We need to balance the scale again. So how do we do that? Well, we need to make sure that we have the same amount on both sides, but these are blobs, they are stuck together, and we cannot just separate them. So if we need another oxygen on this side, we can do that. We can add another oxygen on the right side, but that oxygen on the right side is stuck to 2 hydrogens. So if we do this, we need to take the 2 hydrogens with. We cannot separate it and just, we just use 1 oxygen on the other side. Ain't working. So we cannot separate the H's and the oxygens, as it shows here. We need to take the whole other thing on that side as well. So now we have both of those on that side. Got just 2 oxygens accounted for. But now we have 4 hydrogens. However, what do we need on this side? We need to take probably another blob of 2 hydrogens. Remember, a hydrogen doesn't come alone, gas rule. It's stuck to another one. So we add another hydrogen right here. If we look at this one, now the sucker is balanced. We have the same amount of hydrogens on this side than we have on that side, and the same amounts of oxygen on this side as we have on that side. So what is left? How would I write this equation correctly now up there to make it balanced? Count the blobs, right? Count the blobs and write the multipliers according to the blob count, technical term, in front of my symbols. So with other words, on that side, how many H2 blobs do I have? There's 1 H2 blob and there's another one. I have 2 H2 blobs on that side, and I would write that down, 2 H2s. I have 1 O2 blob right there. I could write this down. Okay. I don't have to because 1 is somewhat superfluous, but I write it down anyway. So 1 O2 blob. On the other side, how many H2O blobs do I have? Okay, 2, of course. And there is your balanced equation. We take 2 H2s and 1 O2 to make 2 H2Os. All balanced. Wonderful. Now, what we haven't done yet is masses. The masses must also be equal, and we're going to introduce a mole to you. Now, though some of you who had chemistry, they know all about it. Some of you have not had chemistry. It is, oh, what is this? I've heard about it. I heard it is very, very difficult. Let's make it super simple for you. They might not tell you this in chemistry. If you weigh a molecule, you have the mass. If you work with moles, you actually just count molecules. So the mole is a bean counting approach. You counting the molecules. Now, how many molecules are there? 1 mole of a substance is the very ridiculous number of 6.02204 times 10 to the 23rd, which is called the Avogadro's number. Do you need to remember this and write it down? You can. We don't do much with it. It just tells you that we have figured out what a mole of a substance is supposed to be, right? So a mole in chemistry is the atomic weight of a substance in relation to the actual amount of the pure substance. Think about it this way. If you play around with marbles, the marbles would be equivalent to the mole. However, if you look at the weight, not all marbles weigh the same. Some marbles are way bigger than others. You know, think about it. If you had a marble and then you had also a bowling ball, there's definitely a difference. A bowling ball occupies much more space, so you would have less beans of bowling balls if you counted the beans or the individual parts than if you just counted the marbles. You would have many, many more marbles for the same space that they would occupy. And this is where the mole comes in. So we're going to play around with the mole a little bit. Let's start with a simple question for you. how many moles of hydrogen are in 10 grams of hydrogen? Now, I realize this is an idiotic question. Hydrogen is a gas. Can you weigh a gas? You could weigh a gas, but to picture 10 grams of hydrogen, it's a little bit difficult. Maybe if I ever rewrite this lecture, I will use something that we can play around with, like iron. But let's stick with the hydrogen. Well, hydrogen is an element and it has a weight, and it's a very, very little weight. So we want to figure out how many moles are in 10 grams of hydrogen. Well, what we're going to do is we're going to look at our periodic table and we find hydrogen. Fairly simple to do. And there we have it. We have the atomic number and we have the atomic mass of 1.008 on that particular periodic table. So what this number really tells us on the periodic table is how many grams of that element we have in 1 mole. Okay, so for hydrogen, I have 1.008 grams per mole of hydrogen. Okay, so if I do the division here and the grams cancel out, you see what's going to happen. 10 divided by 1.008, I get 9.92 moles in 10 grams of hydrogen. And this is how simple it is. This is how you work with the periodic table. You look at the atomic mass and you're going to divide the atomic mass then into the amount of a substance you have, and that gives you the moles. So 9.92 beans, if you want to use an equivalent or a visual. Okay. What about if we use 10 grams of water? Now we're going to run into a little problem. Water is not on the periodic table. Of course, my stupid introductory video that I showed you, age 20. Now it's not on the periodic table. Of course, it was a joke. But it is made up of stuff that is on the periodic table. So how are we going to do this? First of all, we need to figure out, since we cannot read off an atomic mass of water, we can read one off for hydrogen. We cannot read off the atomic mass of water, so we need to figure this one out ourselves. How do we do this? Well, we know the chemical formula is H2O, and we can look to the periodic table and find the masses of all my elements involved, 2 H's and 1 O, right? So what do I need to do is I need to add them together. Whatever is in my chemical formula, I'm going to add it together. So 1 oxygen, in this case, it's listed with an atomic mass of 16. So I have 1 times 16. And I have 2 hydrogens here. And 2 times 1.008 will give me the mass of these systems. Oops, number is above it. Sorry that you can't see it. So 16 plus 2.016 gives you 18.02. That would be the atomic mass of water, basically adding those 2 things together. So this is my atomic mass of water. Okay, so we can play now the same game. 10 grams divided by 1802. This is grams per mole. This is what this number tells us. And what I'm getting is, of course, my grams cancel out, is now 0.55 moles. So you can see what happens. I have much less moles in 10 grams of water than I have in 10 grams of just hydrogen. Well, why is that? Well, the marbles are much larger for hydrogen, 2 H's and 1 O. If you kind of melt them together, kind of make a bigger marble than my hydrogen, very, very tiny marbles. So I'm going to get more marbles on this end than I get here. I get less marbles on this end, so less of a counter. Hopefully this starts to making somewhat sense. Not a very, very difficult concept, so that was fun. Let's try again. How many moles of calcium are in 50 grams of calcium? So what do we need to do? First of all, dig up the periodic table and let's find calcium in it. Here it is. and its atomic number is 20, but the atomic mass listed is 40.08. How do you run this whole show? Well, you know from before, you're going to take the amount of the substance you have and divide the atomic mass into it. So 50 grams divided by 40.08 grams, the grams cancel out, and I get 1.25 moles. Right. Now, in comparison, what if we made a substance called calcium sulfate, and we have 50 grams of that? How many moles would be in 50 grams of calcium sulfate? Well, calcium sulfate, of course, is a compound of some sorts that is not on a periodic table. So in this case, what we need to do is we need to, again, add all the elements that are involved in making calcium sulfate together. So let's look at that formula. What is the correct formula? CaSO4. So it's sulfate polyatomic ion right there, and Ca. Okay, so we need to look up in the periodic table Ca, S, and O and see what we get out of that one. So I'm going to help you here. I'm going to look up the other two. So my O was 16 atomic mass, and sulfur, in this case, 32.07. So we have 1 calcium, 1 sulfur, and 4 oxygens, and we need to sort of add all of this together. So 4 times 16, and my 4 oxygens, 1 times 32.07, and 1 times 40.08. Let's kind of populate this whole thing, add them all together, and then we get an atomic mass of a calcium sulfate molecule atom. That's not an atom, it's a molecular compound, 136.15. Okay, we figured that one out. Really great. 50 grams divided by our 136.15 grams per mole. And unlimber the calculator, my grams cancel out. Now I get 0.367 moles. Again, think about marbles again. If you use calcium, we just have individual marbles all the same size. Now make calcium sulfate, there's calcium in and sulfur and 4 oxygens in it, so a much bigger blob. And frankly, you don't fit as many blobs of those into 50 grams because my blobs are bigger. You can see that when we compare the two. And so you end up with a lower mole count in this case. All right. So let's play around with this for a little bit. Your practice, how many moles are in the following? So 16 grams of sulfur. I give you a little snippet of a periodic table, and you should be able to put this one together. All right, what do you need to do? Take the 16 divided by the atomic mass of sulfur, that's 3207, and look at the chat. He is absolutely right. It's 0.5. If you think about it, it makes total sense. You know, I have 60 grams of it, and the atomic weight is about double of that. So my moles should be half of that, even without a calculator estimate. Let's try something a little bit more difficult. I have 101 grams of potassium oxide. First of all, get the correct chemical formula for potassium oxide. Potassium oxide is not on a periodic table, but then you need to find the building blocks and add them together. And that gives you the atomic mass of potassium oxide. And from then on, it should be a piece of cake. So we'll give you a few numbers here that you can check. And the answer indeed is around 1. I mean, you can sort of do this. The chemistry of potassium oxide is K2O right there. And if I rounded this one, 2 times 40 and 1 times 16 is 96. 101 divided by 96 should be somewhat close to 1, and that would be the resolution. But if you want to calculate the whole thing out, 2 times 39.1 K2, 1 oxygen, 94.20, and the rest is fairly simple. 101 divided by 94.2 gives you 107. All right. Lots of fun. Let's try another one here. Now the grams, of course, cancel out, and you're left with moles as a unit. Okay, how many moles are in 7.50 grams of table salt? Again, we're getting you prepped for better things to come here. We will eventually do something with this in our class. All right, okay, table salt again is not on a periodic table. So at first, what is my formula for table salt? Right? You have that one figured out, doing NaNCl, show you right here, NaCl, 1 sodium, 1 chlorine, add those two together, 58.04, and then of course 7.5 divided by that, and you get 0.129 moles. And so good practice, kind of. Okay, I think I'm getting it. So we're really looking at the beans, the amount of blobs we have there. Okay. Let's go back to our water reaction. And let's figure out, what does this equation mean? Okay. So we have 2 moles of H2 react with 1 mole of O2 to yield 2 moles of water. And this is basically what these numbers mean in front of it. You are counting the beans. How many blobs do you have? 2 blobs of H2, 1 blob, 1 bean of O2 makes 2 beans or 2 bigger blobs of H2O. Now, we can also figure out exactly how much weight or mass we're going to shuffle around in this reaction. So to do this, we need to look up the atomic weights of hydrogen and oxygen, right? And we've done it before. So hydrogen 1.00794, I think I used 1.008 in my example before, and oxygen 15.9994, 16 it was on the other periodic table. Depending which periodic table you have, some rounded up a little bit to make things I think a little easier. Don't have that many decimal points, but we are close. So what is the atomic weight of water? Again, what we need to do is to add all of my individual elements together. So I have 2 H's and 1 O, add them all together, wahoo, and I come up with 18 and some grams per mole. That would be the bottom line. Okay, so for our reaction, how much hydrogen is reaction? 2 H2 blobs. So 1 H is 1.00794. 1 H2 is double of this, but I have 2 of these doubles, which means I need to double it twice. So I actually have 4.03167 grams of hydrogen reacting with how much oxygen? 1 O2 blob, which is 2 times the 15.99, gets me 31.998. And the end is asking for our reaction, how much water do we get? Well, we get 2 H2O, so I need to double my 18.01528 grams. Now comes the clincher. The weight on one side of the arrow should be the same as the weight or the mass on the other side of the arrow. So we need to conserve mass as well. In other words, if you have 4.03176 grams of hydrogen and reacted with 30 1.998 grams of oxygen, you're going to get 36.03 and so forth grams of hydrogen. If you add those two together, 31.998 and 4, you should come up with this number, right? 36, I mean, we're so close to it. You should come up with exactly the same number on both sides of the equation, which means we are indeed balanced. My moles fit and my mass is fitting. So I need to conserve mass as well. I cannot make more mass in a chemical reaction. Things don't get heavier or lighter. Well, you may think, yes, they do. If I have a reaction, well, often my products or reactants are taken from the air or escape in the air. For example, if I burn something, where is the one molecule come from that facilitates burning? Its oxygen. Of course, we're taking it out of the air, and I cannot measure directly how much I'm using because it's not controlled. The fire takes as much as it needs, right? But we can burn something else, magnesium metal. It's actually a beautiful reaction. I wish I could show you. I don't have magnesium metal on me right now. We could burn that, and it makes huge sparks and burns with a very, very bright flame. So what we need to do is first write down the reactants. We have magnesium, right? And now comes, of course, after the obvious, when I burn it, it reacts with something. And that something is, of course, oxygen out of the air. It comes out of the air. And we know that the oxygen we are breathing, the oxygen is in the air, comes in pairs, elemental gas rule, so it floats around as an O2 molecule in our atmosphere. So these are the two things we are reacting in the burning process of magnesium. Okay, so those two react together. And the question is, what would it make? So we need to predict a possible product or products, and probably magnesium oxide, right? What is the correct formula for magnesium oxide? Now I need to remember my valences again. Magnesium is a +2, oxygen is a -2. I can push them together, right? We end up with MgO. But you can see it's not balanced yet, but we have made a prediction. We went through this whole thing. So what do we need to do to balance this whole thing? We need to grab another O on the right side. Well, if we grab another O on the right side, we're running into a problem that this O is attached to an Mg. So it comes with an Mg. We're not done yet, of course. Let's try to balance this equation a little bit. Right. We are off kilter. Let's grab another oxygen that's attached to an Mg. We can do this, and if we do this, then all of a sudden our right side is heavier. So what do we need to do is we need to grab another magnesium. Magnesium, luckily, is a lone rager. It's not attached to anything. So in this case, we can just grab a magnesium. And if we do, then my scale is balanced, and I can count now blobs or individuals, elements. And here we go. How many blobs of magnesium do we have? 2 of those. We have 1 O2 blob, right? And we don't have to write the 1, but we do. And we have 2 MgO blobs. Count those. And here you have it. There is your balanced chemical reaction right there.